Welcome back, everybody. The last speaker for this session is Charles Favre, who works at École Polytechnique in Paris. And he will be speaking on, well, you see the title up there, Lyapunov exponents of non-Archimedean rational maps. All yours.
Thank you very much for the introduction. So I'm very happy to be here. It's also my first time in India. So I decided to talk today about Lyapunov exponent of non-Archimedean rational maps. So the idea is to get some insight on the ergodic properties of rational map in one variable, but defined not over complex numbers in most previous talks, but over a non-Archimedean field. And to try to deduce from this some consequences on families of holomorphic maps. So this is an ongoing project with Juan Rivera Letelier. And so before I turn to the non-Archimedean case, let me describe the situation over C. So K will be my field, so K is equal to C for now. So take any endomorphism of the projective line, F, let's say of degree D at least 2. So any such map is finite. And so if you take any probability measure, mu, so on the Riemann sphere, let me denote this by M1 plus of P1 over C, so probability measure, then you can pull it back by F. And what is its action on a continuous function, phi? Well, this is the integral over d mu of the push forward of phi by F. And the push forward is at a point phi, at a point x, sorry, is the sum at all preimages x prime of x of phi, and here maybe you have to weight this with the logical degree at the point x prime. Okay, so you can, sorry? No, multiply. So this is a number in between 1 and d. It's at least 2 when the point x prime is critical. Okay, so you can check that if phi is continuous, the push forward is continuous, so this makes sense. Okay, so let me now introduce some coordinates. So you pick any coordinates, let's say homogeneous coordinates on P1. So I'm going to use also affine coordinates. So I'm going to denote by Z0, Z1, the homogeneous one, and Z1, the affine one. So that F is given by two homogeneous polynomials, P1 and P0 and P1 of degree D that have no common factors. And so let's discuss what is the pullback of, let's say, the Fubini study volume form on the Riemann sphere, which is, if you want, its restriction to C is the Laplacian of the logarithm of 1 plus z to the square. Maybe you have to divide by 2 here. So if you pull back the Fubini study form, its mass is multiplied by d, so we have to divide by d to get a probability measure. We subtract by the same form. Then this is the Laplacian of the log of, let's say, P0 to the square plus Q, P1 to the square by Z0 a square plus Z1 to the square to the power d, so that this makes this is a well-defined function on the Riemann sphere. And here we have to normalize divide by 1 over 2d. So this is the Laplacian of some function, which is also continuous. Okay, so what you can do is pull back this equation here. So 1 over dn of fn star, we have of the Fibonacci study volume form, well, minus this guy. This is the Laplacian of now a series, sum from k equals 0, let's say j equals 0 to n minus 1, g composed with fj minus 1 over d to the j. And this series here is converging exponentially fast. So in sup norm to some continuous function, g infinity.
Recording in progress.
Yeah, I know. And so, in other words, this means that this sequence of probability measures converge to, as n tends to infinity, converge to some probability measure that I'm going to denote by mu f, and which equals locally Laplacian of g infinity. Okay. So this is a theorem which is due to, let's say, Lubitsch and Frère Magnier-Lopez. Lopez-Magnier, sorry. From the 80s. So this measure is invariant, in fact, backward invariant, sorry. So when you pull it back by f, you get d times itself. It's invariant ergodic, in fact, more, it's mixing. Its support is a Julia set of f. And you can also show that its metric entropy is maximal. In fact, this is a unique measure of maximal entropy. And the entropy here is equal to log d. And so in the title, I'm referring to Lyapunov exponent, so maybe I should discuss what is the Lyapunov exponent of this measure. So by definition, this is the integral of the log of the derivative computed in your favorite Riemann metric, d mu f. And you can show that this is always positive. In fact, it's always greater or equal to 1/2 times log d. Okay, so this is what, so my aim now is to try to discuss what's happening when you replace, for this theorem, when you replace C by some non-Archimedean field. Okay, so so I'm going to focus on, so let me take K now, complete metrized field. And I'm going to assume that this is non-Archimedean. And for simplicity, I'm also going to assume that K is algebraically closed. Okay. It's not really an essential assumption. So what is the basic example? It was already discussed by Professor Shishikura, but let me emphasize this example a little bit more. So suppose that you have a family of endomorphism of the Riemann sphere, which is holomorphic and parametrized by the unit disk. So holomorphic, let's say, let me call it, so holomorphic family over the punctured disk, which is meromorphic at 0. So that might generate at 0. So I'm going to explain that this defines naturally a rational map over some non-Archimedean field that was already defined by Mitsuhiro, and which is the field of formal Laurent series, or it's the completion of its algebraic closure. So in practice, so Ft, what is it? So it's defined by, as before, two homogeneous polynomials, but now the coefficients same for the coefficient here, are holomorphic functions. So holomorphic of a D. So let me call this ring O of D. So I should write this P0 of T and then P1 of T. And so here I'm assuming that when T is non-zero, Ft has degree D. So the resultant, or these two homogeneous polynomials when T is non-zero have no common factors, but when T is equal to 0, then things might degenerate. Okay? So keep in mind the family Z squared plus probably 1 over T. Okay, so having a homomorphic family which is meromorphic at 0 is essentially you're working over this ring, but it's better to work over a field. So what you do is to take the fraction field, and there is a norm, canonical norm on this, and so you prefer to work over a complete field. So what you're going to do is to replace your ring O of D by the ring of a formal power series. Well, okay, I should have said so. This is this sits in the ring of convergent power series, which is a subring of a ring of formal power series, which is itself sits inside the field of Laurent power series. So formal Laurent series. And so, and this field has a natural T-adic norm, which is defined by, so there are several normalizations, but you can define it as being exponential minus the minimum of those indices I such that AI is non-zero. Okay, so for this T-adic norm, this field is complete, but unfortunately it's not algebraically closed. So, okay, so you can look at, I'm not sure, I think it's written this way. It's algebraic closure, which is the field of Puiseux series. Too bad, it's not complete. Okay, so you complete it. And then you get this field that is usually, well, I'm following the notation of Jan Kiwi, denoted by capital L. So which is, it is the smallest non-Archimedean extension of the field of formal Laurent series, which is both algebraically closed and complete. So it's not really important how it looks like. An element in this field is quite explicit, but I won't describe it. Okay, so now what is the upshot of all this discussion is that if you take your favorite family, holomorphic family parameterized by the puncture disk of endomorphism of degree D of P1, then this defines naturally, you can view it as a rational map of degree D over this field L, which is now a non-Archimedean field under this T-adic norm. So to emphasize, so NA here should emphasize the fact that F is defined over a non-Archimedean field, okay? And the degree is the same as the degree of this one. Okay, so in the early, well, 2000, Juan Rivera Letellier and Benedetto have developed, let's say, the Fatou-Julia theory of a rational map defined over, in one variable, defined over any non-Archimedean field. So here, sorry. So let me pick, as before, so K algebraically closed, complete, non-Archimedean. And let me pick F, any rational map of degree at least 2. So you can define Fatu and Julia sets. And it turns out that this Fatu-Julia theory is much better behaved if you work not on classical points, but on the Berkovich identification of P1. So it's well behaved. Let's say it's analogous to the complex theory if you work over the analytification of the projective line of K in the sense of Berkovich. So if you expect me to define very precisely this thing, unfortunately, I cannot say, well, you have to look at the slides of Mitsuhiro, because I was expecting, I don't know, I'm there. I was expecting you to define precisely, but okay. So I'm going to repeat basically what you did and to make a drawing, which will be maybe a little bit different. So that means probably that anyone working on this object have his own mental picture of this thing. But okay, so the Berkovich identification, what you need to know, so it's compact, it's a compact topological space and contains classical points. So the classical terminology for classical points is rigid points. So I'm probably going to use this terminology later on, rigid points. So what are classical points? So I'm going to denote this by P1 parenthesis K. So there's those points, the usual points, right? So Z0, Z1, whereas Z0 and Z1 are in K. Well, not two of them 0. Okay, so maybe I should say in K square minus 0, 0. So in fact, the rigid points are dense inside the Berkovich space. So what is very important is that it's an R3, meaning that any 2 points can be joined by a unique geodesic if you want. So it's one-dimensional. It has no loop. And it's quite important because then you can develop potential theory. So Becker and Rimoli, well, many people, and Matthias Jonsson, Trillier, etc. So proved that you can develop a general potential theory over an R3, meaning what? That you can take the Laplacian defined subharmonic function and so on and so forth. So what I'm saying here is that we're going to define this measure mu f exactly in the same way as we did in over the complex. Okay, so when f is a rational map of degree d, this is also finite, and so and analytic in the sense of Berkovich theory, and so you can define a pullback operator on continuous functions. Sorry, a push forward operator on continuous functions. Hence a pullback on measures. So what lies behind is that you can define also a local degree. So at a classical point, this is standard definition. But at a non-classical point, you need to work a little bit. So to use Berkovich theory to define it properly. And once you have this, then you can check that push forward a continuous map remains continuous, and so you can pull back probability measures. Okay, so now I need to construct this measure mu f in this non-Archimedean context. So before, what we did, we were pulling back smooth forms, smooth positive forms. So here it doesn't really make sense. So I'm going to explain by what I'm going to replace this measure mu fs. So let me draw my fantastic picture of. So I'm not a computer, okay? So I'm not as fast as It's not going to be very precise. So this is supposedly the Berkovich line over over K. So what Mitsu said is that this is a tree, and these points are boundary points, endpoints of the tree. So let me put them in red. Okay, some of them, not all of them. Okay. And you also have the interior points. So the complement, I'm denoting by H index K. It plays the role of the hyperbolic space. So it carries the canonical metric and so on. So there are interior points. And so here I'm cheating a little bit, but these interior points, they correspond more or less bijectively to balls for the projective metric. And in particular, so you can look at the point which corresponds to the unit ball. And this one is if you want the central point, so this is what I draw in yellow, and this is called the Gauss point. Okay, and so what is going to play the role of my Fubini study volume form here is the delta mass at this Gauss point. Okay, and so when so if you plug in this potential theory developed here with this thing, and if you pull back this delta mass at the Gauss point divided by d minus the delta mass at the Gauss point, you get a formula which is very much the same as in the complex setting. This is the Laplacian of log. So you replace the sum of the squares by the max. So log of max, norm of P naught, P1, divided as max, Z naught, Z1 to the power d, maybe here 1 over d. Okay, so you can repeat exactly the same construction as over the complex, and you get this theorem. So 1 over dn fn star mu fs converges to some probability measure, which is totally invariant, whose support is a Julia set. And what I want to say here, yeah, which is mixing, again. And for which, so the rest is not clear, but for which at least you can define the Lyapunov exponent. So here a statement is that this quantity, so if you look at the integral of the log of the norm of the differential d mu f, this is finite. Okay, so where does it come from? It comes from the fact that locally mu f is a Laplacian of some continuous functions, and so we can integrate any log of modulus of analytic function.
I have a question.
Yep.
You seem to have missed something. I thought that the dynamical system that we get acts on the projective space.
Yeah.
Now you've added all these interior points.
Yeah.
So.
Well, this is okay. This is. I'm not sure what you mean by projective space. You know, P1 over C. If you look, if it is a projective space, it's an algebraic variety, so it's with the Zariski topology. But I don't think that you want to do dynamics on a projective space, algebraic space with its Zariski topology. So you think of it as a Riemann sphere. It's no longer an algebraic space, right? It's a Riemann surface. So here I'm doing exactly the same. I'm putting an. So the only problem or things that is a bit different is that I'm adding a lot of points.
I think his question was, how does F extend to P1 now?
Canonically, well, if you want, I didn't define this, so okay. So its action on the classical point is the same, and I'm just claiming that it extends. So this is dense in this. It extends naturally and continuously on here. It's just F is algebraic, so you take the analytification of this, so they extend naturally at continuous map, even analytic maps. Then maybe the next question is, okay, fine, but now it's a tree. How does it act on the tree? Okay, sorry?
Yeah, how do I think of the derivative function?
No. It's not. Okay, so what's going to happen is that if you look at a segment inside the tree, you can subdivide the segment to finitely many segments, and the map is going to be, so there is it's going to be injective on each of these subsegments. So it maps a segment to another segment, and injectively, and in fact, here what I said is that there is a canonical parametrization, the canonical metric, and for this canonical metric, the the map explained by an integral factor. This integral factor plays the role of the local degree. Okay, so I'm very fast. I'm not going to write this down here, but so this is what's happening.
Sorry, one more question.
Yeah.
Such classical points are dense. If you're a bit boundary, but see something there.
What?
Such classical points are dense, but then in your picture you said that they're boundary points.
Interesting. So here, okay, I'm a bit fuzzy here. Okay, so it's not very precise. It's an endpoint in the sense of the tree, in a tree sense. Okay. When I say interior points, this was because I put quotation marks, but there are no interior because the endpoints are dense. So, okay. Okay, what I want to say. Okay, so for now on.
So in fact, the endpoints constitute the space of ends of a tree, understood as a traditional way, traditional sense, right? So these are the Freudenthal ends.
What? I'm sorry.
If you look at the equivalence classes of connected components
Of the complement, blah, blah, blah. Yeah. And so here, when you're in a tree, you can define the set of directions if you want. And so endpoint means that you have only one direction popping out from your point. Okay? Okay, so from now on, I'm going to add one more assumption to K. I'm going to assume that the characteristic of its residue field is 0. Okay, so I'm not going to define what this is, but this is true if K is equal to L, because in that case, K tilde is the field of complex numbers. But you have to keep in mind that this is not true in general. And there are very important examples for which you cannot apply what I'm going to say. So, for instance, if K is any extension of QP, like CP, or if it's have positive characteristics that FP of T and its extensions. Okay, so the aim again is now to try to understand when these two statements are true in the non-Archimedean case setting. So the first fact, which I guess is due to Okuyama, is that under that assumption, so let me rewrite it, the residual characteristic is 0, then the Lyapunov exponent of mu f is non-negative. So let me explain how you get this. So in fact, in characteristic 0, you have, at least where f is a polynomial, you have this nice formula for the Lyapunov exponent. It is a log of the norm of D plus the sum of the green function, which I didn't define, but evaluated at all critical points. So here, except infinity, right? So this is, well, this formula is true over C, but it's true over any field of characteristic 0. But here you have to be careful. Here, this norm is the norm of your field. So over C, of course, the absolute value of D is big. But if the residual characteristic is 0, then this number is 1. Okay, so this might be 0. And if the residual characteristic is P, and if P divides D, then this norm is negative. Okay, so in general, you can expect the Lyapunov exponent to be negative. This happens. But at least under my assumption here on the residual characteristic, this will not happen. And so this is going to be greater or equal to 0. I mean, this green function is all non-negative, right? So this is what happens for polynomials. For rational functions, so what Okuyama proved is he proved that in characteristic 0, you can approximate this Lyapunov exponent in terms of the multipliers of the periodic points, periodic cycles of f. And so it deduced from this, this inequality. So here, approximate by multipliers. I'm not explaining much, but okay, I'd like maybe to so there are some nice work by Ni and Jacobs discussing a little bit when this can be true, when you replace also this measure by some other ergodic measure and so on and so forth. Okay, so now let's move on. So we have this inequality. So we have two options. Either the Lyapunov exponent is actually positive or it's 0. So what we're going to see is that we have a very strong dichotomy. So if this is positive, then f looks, whatever that means, like, okay, or maybe I should not say this, but so the situation is very similar like in the complex. So similar as the complex holomorphic situation. But sometimes this Lyapunov exponent is 0. And then what I'm going to explain is that you have some kind of rigidity. So it's not going to be too rigid as in the complex setting, but still, at least the dynamics is going to be very special. Okay, so let me discuss this first case, where the Lyapunov exponent is positive. And so the first lemma is that in that case, well, this measure mu f charges only classical points. So it does not put any measure on the interior on this hyperbolic space H of k. Okay, so how does it work? So this comes from a very important invariant. So you can define a so-called diameter. So this is a function in the on the analytification on the Berkovich projective line to 0, 1. Its value is 0 if and only if x is a classical point, and otherwise, so I'm not going to define this very precisely, but what I said is that x, when it's not a classical point, is attached to some ball, and here I'm going to take the diameter of that ball. Okay, so for instance, the diameter is equal to 1. Well, this is exactly a situation where x is equal to the Gauss point. Otherwise, you're in between. And now we have this beautiful formula that, in fact, the derivative, the norm of the derivative is some kind of cocycle. So it's if you look at the diameter of f of x divided by the diameter of x, what you obtain is a norm of the derivative. So if you suppose that a Lyapunov exponent is positive, if you iterate this, this thing here, so apply this for Fn, this number is very big, at least for x generic point on the support of the measure. So this thing is very, very big. So this thing is bounded, so it means that this has to be equal to 0. Okay, so now probably I can put like ... Okay, so theorem. So if okay, let me change. So f p1k residual characteristic 0, and now I'm assuming that a Lyapunov exponent is positive. Then you can show that this is the unique measure of maximal entropy. Whoops. And if you want to, I didn't talk about this, but you also have the important fact that rippling orbits, classical orbits, equidistribute to mu f. So what it says is that, in fact, once you know this and you know that it charges only classical points, you can basically repeat the argument from the complex setting to the non-Archimedean setting. So basically what you have to do is to construct many invariant preimages on small balls and that are contracting. And so this is exactly what you can do in this setting. Okay, so let me explain one consequence of this. I'm not sure. So I'll have like 22 minutes, something like this, right? Yeah, well, okay. So one consequence of this for holomorphic families, meromorphic families. So Ft, a meromorphic family parameterized by the unit disk. And so recall that we, attached a natural rational map defined over this extension of the formal Lorentz series, L. So now let me assume that this Lyapunov exponent is positive. And so the conclusion here is that you have many, okay, well, I have something about the entropy. I'm going to focus on the next statement, that you have many rippling orbits. So now this has a consequence for the complex family itself. So let me explain this. So let me fix any point, let's say T0 in the puncture disk, and pick a point P, which is periodic for Ft0. So in general, you cannot exactly follow this point by the disk, but after base change, you can. So let me assume that you can follow that point. That is, you can find a meromorphic map. T goes to P of T, such that P of T0 is my original point P, and this point is periodic for Ft. So Ft of P of T is equal to, Fnt is equal to P of T. Okay? So a corollary of the statement on the right board is that, so at least you have a lot of rippling non-Archimedean orbit. And so it's going to mean that for a lot of periodic points like this, the multiplier at P of T is going to explode. So corollary. So again, this assumption is essential. Then if you look, so let me write it down. You look at the set of periodic points, let's say fixed points of Fn T0, and such that, the norm of the nth derivative at T of P of T explode. So like C kappa to the n for some C positive and kappa at least 1. Okay, so this tends to 1. Okay, again, so what this means essentially is that most periodic points, the multiplier is going to explode. Okay, so now let me discuss the second case, which is more interesting, which is when the Lyapunov exponent is 0. So again, so I'm returning through my situation where k is quite general, not necessarily equal to L, and f is a rational map of degree d on defined over k. Okay, so again, this assumption of residual characteristic is essential. And so here we have a complete description of the dynamics. So let me state it in two, split the main statement in two. So first theorem says that, okay, if mu f charges a segment, I don't have much space, so let me summarize. So I here is a segment in HK. Then the conclusion is that, so this is a rigidity I was alluded to. So F is either affine Bernoulli, I'm going to explain these terms, or has potential good reduction. And the second statement is that, okay, so here you have no connection with this assumption, right? So the second statement is that if k is equal to 0, then it has to charge a segment. So in other words, if does not charge any segment, then in fact the exponent, Lyapunov exponent, is positive.
Sorry, Charles, I'm
Yep.
still catching up with what you had written.
Before.
Can't
Yeah.
read your. So
I should have prepared the slides.
said explode,
Thank you.
I assumed you were going to say as t goes to 0 or something, but you don't have a t dependence.
Okay, so let me draw a picture.
No, can you just make the mathematical statement real picture? Sorry, what was the explode? Here you just have it exploding as a period.
So yeah,
T,
no. What I'm saying here. Yeah, I'm too fast. This was the t-adic norm, I guess. Yeah. The t-adic norm. Okay, so this means, yeah, sorry. So this means, okay, so here I have to, so this means that if you take the log of this and you divide by log of t minus 1, this tends to a constant, so lim blah blah blah, inf or sup or inf is greater or equal to c kappa to the n as t tends to 0. Okay, anyway, so you look at this, this f n t prime p of t, basically this is a meromorphic function at 0. It has a pole. What I'm saying, it has a pole. Okay, so it's really meromorphic, so it has to explode. It cannot be bounded. So here I'm much more precise, saying that in fact you have some kind of uniformity with kappa and this constant c, but it's not really important. Okay, so I need to define these two notions here. So affine Bernoulli and potential good reduction. So maybe let me start with this notion of potential good reduction. And here again, it's probably easier to discuss in the case we have a meromorphic family. So suppose it's a good reduction, or potential good reduction. So again, suppose that we work over L, and that F is defined, arise from a holomorphic family of endomorphism of a Riemann sphere of degree D. Then to have potential good direction means the following. So what you can do, for any T, you can look at its class in the moduli space that I'm going to denote by rat D, the moduli space of all rational functions of degree D, modulo conjugacy by Möbius transformations. So one knows that this space is affine. So to have potential good deduction is saying that this sequence remains bounded. So in other words, you can make a change of coordinates, a conjugacy depending on T, such that your family, when T is equal to 0, does not degenerate. So F0 becomes stays of degree D. Okay? And so we have a theorem. So we prove that several equivalents. Okay, maybe maybe I should not say this because probably some of the equivalents were proved also by some other people. But okay, so F has potential good deduction. So this is equivalent to say that mu F is very special. In fact, the direct mass at a point. So it's direct mass at a point X, which is an interior point, in fact, much more. X is in the orbit of the Gauss point under the action by PGL2. And this is equivalent to say that the entropy, the metric entropy of mu F is 0, which is equivalent to say that the topological entropy is equal to 0. Okay, so potential good reduction means that at the ergodic level, there is basically nothing to say. The Julia set is a point, so it's not very interesting. At least, so what this means is that non-Archimedean dynamics does not tell much about this kind of situations, which is kind of expected. So what is affine Bernoulli? So the definition is a bit more complicated here. Okay, so affine Bernoulli means that the Julia set is going to be included in some segment. So there exists some segment I inside the complement of the points, of classical points. And this segment can be, and so inside this segment, you can find finitely many subsegments. Okay, I should not say K, I1, I blah, 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 L. I1, IL, such that their closure, at least their interiors are disjoint. So they can intersect, but only at boundary points. And the map F sends each of these segments to I surjectively. And there are restrictions. So remember, this HK came with there is a canonical metric on this space, and for this canonical metric, so F is affine, and the slope is an integer. Let me call it a D index I, which is at least 2. So between 2 and so we're going to see that it cannot be too big. So situation is like this. Oops. So it maps I1 to I with some slope, D1, slope D2, etc., DL. So there are further conditions here. So just like in the picture, the slopes or the sign of the slopes are alternating. Okay, so here I should have said plus or minus. So you have alternating signs. And the sum of the degrees of the di is equal to d. Okay, so let me, so there are many examples of such things. And also among, there are examples arising from meromorphic families. So the most famous one was, let's say, first considered by Macmillan. And then you have a lot of works by Divani. So on this family, so you look at ft of z, which is z to the k plus t the, to the m, where k and m are integers, and both at least 2. So when you look at fna of this, well, this is affine Bernoulli. And in fact, in that case, so it looks like this. So you can find a segment, it's very explicit, a segment which is in fact a subsegment of the line joining 0 to infinity in P1, where here you have a slope m, I think, here slope k. So m plus k is equal to d. Okay, so what can you have many more examples, of course, of this. So what can we say about, let's say, algebraic properties of such a map? So the first thing to notice is that if you pick, so the Julia set of F is a subset of I. In fact, it is equal to the set of points inside this big segment that remains, whose orbit is contained in I for all iterates. So this is the intersection of A minus n of I non-negative. So basically you have two cases. Either you have a gap here, and then this set is a counter set, or you don't have a gap, and then the Julia set is equal to the full interval. So you can show that, well, you can compute the entropy, the topological entropy of F. This is the log of the number of pieces that appear here, so it's log of L. And interestingly enough, so L is at least 2 by definition, and because of this, this is less or equal to d over 2. So it's less or equal to fraction, well, the integral part of d over 2. But it's a log of an integer. And, well, I can say more, but you have to be careful because in general, so mu f, the metric entropy of mu f, is not log of L. It's a sum. So I wrote this down. So dj over d log of d over dj. And this is equal to L if and only if all dj's are equal. Okay, so in general, so this is less or equal. It could be strictly less. So in that case, the entropy, the non-Archimedean entropy is log 2. But if you compute this number, this is strictly less than log 2. Well, okay. Well, fine. This is a strict convexity of, or concavity of minus x log x. Okay, let me give one consequence of, so suppose that now you have a holomorphic, meromorphic family. So suppose that this is equal to 0. So the theorem says that Fna is affine Bernoulli, or has potential good deduction. So let's say that assume that f of t degenerate to exclude the fact that it has potential good deduction. Then in that case, we can, so what we see that the Julia set is fully contained in this in this interval. So it implies that all periodic points that are classical, there are many of them, are indifferent in a non-Archimedean setting. So it implies that the multipliers of, let's say, fn t p of t, as before, remains all bounded. So what I'm saying is that if you find a family for which the Lyapunov exponent of the non-Archimedean dynamical system is 0, then it implies that you look at any periodic cycle, its multiplier, as t goes to 0, has to remain bounded. So here I have to mention this beautiful work of Yusheng Luo. So what he proved is that, okay, if the residual characteristic is 0, etc., if all periodic classical or rigid cycles are indifferent or non-repelling, then this implies a fine Bernoulli. And so what I'm explaining here is somehow a very much stronger version of what you obtain. And this is a crucial step in this classification of hyperbolic components in RAD-D, for which you can find a sequence tending to infinity for the multiplier stays all bounded. Okay? Corollary of this, so it's just a curiosity. But if you assume that D is equal to 2 or 3, if you have a holomorphic family like this, then you have a criterion for when this tends to infinity or not. Okay, let me say, this way. So f tends to infinity in the rational, in the space, the moduli space, if and only if there exists a cycle, periodic cycle, whose multiplier explodes. So why is it true? It's because here I find Bernoulli. You have this condition here, and the di are at least 2, and you have at least 2 of them, and so d has to be at least 4. Okay. So of course, for d is equal to 2, this is not big news, because by Milnor theorem, we know that RAD2 is parametrized the multipliers at the fixed point. Okay, so if you go to infinity, at least one of them is going to explode. For d equals 3, I don't know. Maybe someone knows, but it's a consequence of this. But here, I'm not saying anything so about the period that we have to take. Probably you only need to check for period 2. Okay. I'm almost done. So let me start the proof. Yeah, and I see that I was so clever that I erased the 2 results. Yeah, maybe I should stop here. Yeah, thank you.